Hi everyone. Today we are talking about section 1.6, which is called powers, polynomials, and rational functions. This one will be a little bit shorter than the last few. We're just going to talk about three different types of functions: powers, polynomials, and rational functions. So starting right in on the first ones, power functions. A power function is just a function that has a certain form that looks like this. It's a constant times your variable x to some power p. And in most of this section, we're going to be looking at powers p that are positive whole numbers, although they could be anything. I want to point out now that k and p are just constants. So compare this to an exponential function like we talked about in section 1.2. Exponential functions look like this. We have a constant times a constant to our variable x. So the difference is that in the exponential functions, the variable x is in the exponent. It's the exponent that changes. And in the power functions, it's the base, and the exponent is just a constant. So some examples of power functions, something like 3x squared. You've got your 3 in front, that's your k. 2 is your power, that's 2, and x is your variable. Other power functions are negative 5x to the 10th, or 1/2 x to the negative 3, so that's an example with a negative power, or pi times x to the 1/2. That's a fractional power. So in most of this section, we will have powers that are positive whole numbers like 2 and 10, not negative numbers or fractions, but they are included in the definition of power functions. Let's see what their graphs look like. So we want to see how to graph a function like k times x to the p. And again, we're assuming that p is a positive whole number here. Well, if k is a positive number, then there's a difference between the even powers and the odd ones. The even powers have this general shape here, where we kind of recognize this quadratic shape. A function like kx squared looks like that. And as the power goes up but stays even, they get narrower and narrower. So here's kx to the 4th, kx to the 6th, and so on. If p is odd, then they're kind of the same, except the part to the left now is below the axis instead of above it. So you might recognize a line. This is kx to the 1. That's just a line. Or kx cubed. Looks like this. That might be a function that's familiar to you. And as you raise the power to higher and higher odd powers, again, they get more and more narrow, but it's one below and one above that get narrow. So kx to the 5th and then kx to the 7th would be in here, and so on. Now that was all assuming our constant out front is positive. If k is negative, we get the exact same picture, but flipped upside down. And we know that from section 1.3 that taught us about transformations. If we're multiplying by a negative number, we get that vertical flip. And that's what this part here is telling us. So that's the general shape. Now, how do we know that the behavior looks like that? Let's think about an example for a minute. Let's think about f of x equals negative 3 x to the 7th. So based on our picture from the last slide, x to the 7th would look kind of like this. And then because we have the negative in front, it's going to get flipped around and look something like this. But that's just because we had the picture. How do we know? Well, when we're asking that question, what we're really asking is what is the behavior of the graph as we go off to the left and off to the right. And by off to the left, we mean all the way to negative infinity on the left and all the way to positive infinity on the right. And this is leading into the topic of the next couple of sections called limits. So let's rephrase this question in a slightly different way that's going to foreshadow some of our future sections. Rephrasing this, we could ask, what is the limit? And I haven't defined this, and I won't in this section, but maybe it will make some intuitive sense. What is the limit of the function as x goes to infinity? So this arrow here, this says x goes to infinity. And when we say limit, we really mean behavior. So this is another way to phrase the question. What happens to f as x goes off to infinity? That means off to the right really far. And on the left-hand side, we could ask, what is the limit of f? So what's the behavior as x goes off to negative infinity? That means going really far to the left. So how do we know that for this particular example, as we go off really far to the left, we get positive, and then as we go to the right, we get negative? Well, we can just think about what happens on the left when we plug in really big negative numbers, and on the right when we plug in really big positive numbers. So here's kind of like a a fake calculation without real numbers that should illustrate what I mean. For this example, if we want to know what happens as you go really far to the right, well, if you're thinking really far to the right, you can think about plugging in a very big positive number, maybe 1,000 or 10,000 or a million or a trillion. Obviously, a trillion is not infinity. You'll never reach infinity. But if you plug in a really, really big number, what happens? Well, let's think about what happens if we take f and we substitute a really big positive number. So we take that big positive number, I'm abbreviating it BPN here, and we plug it into our function. So negative 3x to the 7th becomes negative 3 times big positive number to the 7th. Well, what happens if I take a big positive number and I raise it to the 7th power? I get an even bigger positive number, a very big one. So now I'm taking a very, very big positive number and multiplying by negative 3. Well, that means it gets 3 times bigger, but also because the negative sign, it becomes negative. So the result, if I look at f of a big positive number, is some big negative number. So that's telling me when I plug in really big numbers, a trillion, a quadrillion, a Google, as big as you can think, the result is really big negative numbers. So as I go off to infinity, on the right in my graph, I go down to negative numbers. On the flip side, if you want to know what happens as you go to the left, that means you're plugging in bigger and bigger negative numbers, negative 1,000, negative a million, negative a trillion, and so on. So what is f of a really big negative number? Well, plugging it in, that's negative 3 times a big negative number to the 7th. And now we have to think, what happens when I raise a big negative number to the 7th? Well, if you have a negative and you raise it to a 7th, it stays negative because that's an odd number of negative signs. So we get negative 3 times an even bigger negative number. And that means we have a negative times a negative, which makes a big positive number. So plugging in a big negative number means I get a big positive number, and that tells me as I go off to the left, I go to infinity. So this kind of fake arithmetic doesn't tell us what happens at 0, 1, or 5, or negative 10. It tells us what happens in the really long run as x is very, very big negative or very, very big positive. So this kind of gives us that answer. It tells us that the limit of the function as x goes to positive infinity, that means going off to the right, is negative infinity. That means it goes down. And the limit as x goes to negative infinity, that means as we go off to the left, is positive infinity. That means it goes up. Now, you might wonder, what is the difference between power functions and exponential functions, other than the form? So we already said that power functions look like k times x to the p. The variable is in the base, not the exponent, whereas exponential functions look like a constant times a constant to a variable. So the variable's in the exponent there. Well, the answer is that exponential functions get way, way, way bigger. They grow much, much faster than power functions, but the caveat here is important, eventually. Sometimes it might take a while to see where exponential functions start getting bigger. So let's go into our graph real quick. So here's a graph of 2 to the x in red, that's an exponential function, and x cubed in blue, that's our power function. I've restricted them to only show when x is greater than or equal to 0, just to kind of eliminate some of the other stuff in the picture. And I'm also showing a point on each one. So at the moment, my slider for a here at the bottom is at 0. So I'm showing where 0 is on both of them. And you see at the beginning here, the red one is bigger. So the red one is 2 to the x. So when I'm plugging in 0, the exponential is bigger. But if we look at this picture, it looks a little bit confusing. It looks like the opposite of what I just said. Somewhere right around here at about 1.3, 1.4, and by the way, you could use logarithms to figure out exactly where that changes. Now, suddenly, the blue one is bigger. So I told you that exponentials were bigger eventually, but here it looks like they were bigger to start with, and then x cubed took over. Well, let's zoom out. We're zooming out really, really far. And it's kind of hard to see. It looks like the blue one is still bigger. And actually, I'll tell you that they do switch places, but they switch places kind of around 1,000. And you can zoom in all you want, but it's going to always look like these two very tall vertical lines. So a better way to see this is, let me go back here. Let me zoom out again. I'm going to rewind our slider here and let it play forward. And you'll see the blue one is x cubed. So at first, not much is happening. That blue one, that's x cubed, really, we saw, starts to beat 2 to the x. And it keeps beating it for a while. It even speeds up. But eventually, it takes a little bit. Eventually, the exponential function gets up to speed and blasts right past the polynomial. So sometimes it might take a while for that to happen. In this case, they intersected somewhere around here, I think. In fact, that's where. So 9.94. So that's the value of x where they're finally equal. But it happens at a height of 981.97. And then once you get past that, once you get to 10 and beyond, then the exponential is bigger. So it's always bigger and much, much, much bigger, but sometimes it takes a while to reach that status. So that was power functions. Next up, we're going to talk about the second thing that's in the title for the section, which is polynomials. Now, a polynomial is really just a bunch of power functions added together. So here's an example of a polynomial. And you've been seeing these in algebra and pre-calc for years, even if you didn't call them this. Here's an example of a polynomial. You can see that it's 4 power functions added together. Negative 3x to the 4th plus 5x squared minus 2x plus 1. Now it's missing an x cubed term. That's fine. That just means that the coefficient for x squared, or x cubed, is 0. There's like a 0x cubed hidden in there. So we've got these 4 terms. Each one of them has a constant in front. In fact, another word for these, I just said coefficients. These are the coefficients. And then we've got the powers. That's the x to the 4th, x squared, x. This is really secretly an x to the 1. And even though we didn't write it, that's an x to the 0. The general form of a polynomial looks kind of like this. Now, this looks complicated, but I promise it's not as scary as it looks. This is just saying that you've got some largest degree, some largest power, a sub n times x to the n, so a constant times your variable to the largest power. Then you've got some next one to the x to the n minus 1 power. We've got a dot, dot, dot saying that we've got a bunch of in the middle here. Then we've got this quadratic term, the linear term, and what we call the constant term. So a bunch of powers of x, each one of them having some coefficient in front. Now, a word that I used before just a minute ago but haven't defined yet is degree. The degree of a polynomial is that largest power. So that's a degree n polynomial in this general form. This is a degree 4 polynomial. When we talk about quadratics, those are degree 2 polynomials, and so on. Now, we looked at shapes of power functions, and those all looked kind of like this to varying degrees of steepness, or this. Polynomials can be a little bit more complicated because you have those lower terms that can affect the behavior. So the key to understanding the general shape is that if you have a degree n polynomial, then it can do a U-turn. It can turn around up to n minus 1 times. Now, it doesn't have to turn around n minus 1 times, but the most it can turn around is n minus 1. So let me show you a couple of examples. A degree 1 polynomial, well, that must be a line. By our formula, or by our general form, that's going to look something like a1 times x plus a0. And even though we didn't write it in the mx plus b form, you can see that it's the same. So degree 1 polynomials, that's at n equals 1. Our fact here says that they can turn around up to 0 times. So that means they can't turn around. And that makes sense. We know what lines look like. They either always go up or they always go down. They can't turn around. On the other hand, degree 2 polynomials, that's n equals 2, they can turn around up to 1 time. So this one does that. It goes down and then it goes up. Alternatively, they could go up and then down. Now, if you think about it, a degree 2 polynomial has to look like one of those two. It can't turn around 0 times. So it either turns around once and looks like this, or it turns around once and looks like that. Degree 3 polynomials, that's n equals 3, so they can turn around up to twice. And in fact, it turns out that they can turn around 0 times or 2 times, but not 1. So they either look like this, Now you notice this one doesn't turn around. It kind of comes to a stop, looks like it's about to turn around, and then goes back up. Or they can do two turnarounds, which means they go up, and then they turn around and go down, and they turn around and go up again. And this could be the reverse too if you have a negative sign in front. So they could go down, and then up, and then down. So that's the general shape. Let me show you one more example. If you had something that was degree 5, that means it can turn around at most 4 times. So it could look like up, and then down, and then up, and then down, and then up. So that's 1, 2, 3, 4 U-turns. Now we can try to identify the shape of a polynomial with a couple of different features. One of the important ones is the x-intercepts. We talked about y-intercepts when we were studying lines. The y-intercept is where the line crosses the y-axis. Well, x-intercepts are just where the shape, the curve, crosses the x-axis. One important fact that, again, you may remember from algebra is that if you have a polynomial p of x and it touches the x-axis at some value c, and that could be either touching and then bouncing off or touching and going through, then x minus c must be a factor of the polynomial. So let me show you what I mean here. Here's an example from the book. They give us this shape, and they ask, can we find a degree 2 polynomial that looks like this? So basically, our job is to find the equation for p of x, and what we're given is that we have x-intercepts at -2 and +2, and a y-intercept at 4. So we can use that fact from the last slide. If we have an x-intercept at 2, then that means our polynomial must have a factor of x minus 2. And why is that? It's because having an x-intercept of 2 means that if I plug in 2, then I must get 0, right? This is the point 2, 0. So if I plug in 2, I must get 0. That means we have a factor of x minus 2, because now if I plug 2 into this, then that factor is 0, and then I have something times 0 times something, which is 0. On the other hand, we also have an x-intercept of -2. So that means that I also have to have a factor of x minus -2, or canceling the negative signs, x plus 2. So that means my polynomial has a factor of x minus 2, a factor of x plus 2, but if it's going to have degree 2 means it can only have 2 factors. If it had a third factor, if it had this one, and a third one, then we'd have an x cubed when we multiplied it all out. So it can only have 2 factors, and we found 2 of them from the x-intercepts. So all that's left, the only other thing that we might not know, is what multiple out in front we have. So right here, I've written our polynomial as a factor that we don't know, k, times the factor that we derived from the x-intercept of 2, times the factor that we derived from the x-intercept of -2. So how can we find this k? Well, we used the information of this x-intercept and that x-intercept, but information that we did not use yet is the y-intercept of 4. So that means this is the point 0, 4. When we say 0, 4 is on the graph, that means when you plug in 0, you have to get 4. So let's plug in 0 for x into this almost complete answer, and we know that we should get 4, and that will let us solve for k. So p of 0 should equal 4. That means 4 equals p of 0, and if I plug 0 in here, we get k times -2 times +2. So that means p of 0 is -4k. So what we know now is that 4 equals -4k, and if we divide the -4 over to the other side, we get k equals -1. And that was the only unknown that was left here, and so now we know it, and we can plug it in, and we have our final answer. This polynomial, p of x, is -1, or just negative, x minus 2 times x plus 2. I'll show you one more example now that's also in the book. This one does 2 U-turns. Turns around here and turns around here. And it asks, can we find a cubic? Cubic is a word for degree 3 polynomial that looks like this. So what do we know? We know 3 x-intercepts, -3, 1, and +2, and we know a y-intercept of negative 12. So we're going to follow the same kind of logic. We have x-intercepts of negative 3, 1, and 2. That means that because of the 1, we have a factor of x minus 1. Because of the 2, we have a factor of x minus 2. And because of the negative 3, we have a factor of x minus negative 3. That's x plus 3. So we have 3 factors already, and it's a degree 3, so that must be all of them because we can't have more than 3. And that means the only bit of information we don't know yet, once again, is this constant in front. So we used that intercept, and that intercept, and that means the only information we have left to try to use is the y-intercept. So this y-intercept, this is the point 0, comma, negative 12. That means when I plug in 0, I need to get negative 12. So negative 12 equals p of 0. When I plug in 0, I get k times negative 1 times negative 2 times 3, which is positive 6k. So negative 12 equals 6k, and if I divide the 6 over, that means k equals negative 2. So that's the answer, and we just plug it in. Our polynomial is negative 2 times x minus 1 times x minus 2 times x plus 3. So same basic logic as the last one, except this one was degree 3 instead of degree 2. Now the last topic, the last of those 3, are rational functions. These are more challenging in general, so we're not going to talk about them in as much detail yet. We will talk about them a little more in later sections. Mostly the definition for right now is the key part, and we'll show one easy example. A rational function is just a fraction of polynomials. So a rational function r looks like this: p of x over q of x, where, and I should have written this before, but let me write it now, where p of x and q of x are polynomials. They are a little bit harder to graph, and the reason is that now that you have something in a denominator, you can get weird behavior. Because remember, when a denominator gets small, when it gets close to 0, if the denominator is small, then the whole fraction is big. So that can cause things called vertical asymptotes. Here's just one example of a graph. This one doesn't have one. This is a rational function. Now you might object and say, whoa, it's obvious that the denominator is a polynomial, it's a degree 2, but the numerator is just a constant. Well, remember, a constant is a polynomial. A constant is just a degree 0 polynomial. So that's fine. It's a boring one, but it's still a polynomial. Well, if we were trying to graph this, what information can we glean from it? For starters, we can glean that it's an even function. Even functions mean graphically that if I flip them over the y-axis, I get the same thing. But they also mean algebraically that f of negative x equals f of x. And you can see here that if you plug in negative x, it immediately gets squared and the negative sign vanishes. So the algebra tells me that it's even, and the definition of even tells me that now it's going to be symmetric around the y-axis. So that gives me a hint. I also can plug in f of 0 and see what I get. That's always a good thing to do, is plug in some numbers and check the values. And especially plugging in 0 usually gives you some good information. So if I plug in 0, I get 1 over 0 plus 4. That's 1/4. Lastly, I want to figure out what happens as x goes very far off to the right and very far off to the left. So using the same kind of trick as before, what happens if I plug in a very big positive number? So that means we're plugging in a big positive number. We're going to square it, so that's an even bigger positive number. You're going to add 4. Now, if you have a really huge number and you add 4, that doesn't really make much of a difference. So really, we've just got 1 divided by a really big number, a big positive number. So now you have to think, what is 1 divided by a very big positive number? It's very close to 0. 1 over big positive number is a positive very close to 0. And you should have some intuition. You should just know that, right? 1 over a million, 1 over a billion, 1 over a trillion gets very, very close to 0. So that tells me, it doesn't really tell me everything about this shape. That's not enough information for you to reproduce this picture exactly, but it's enough for you to understand the picture. At 0, it's 1/4. And if you wanted to, you could plug in other numbers. What is it at 1? It's 1/5. So at 1, it's like 1/5. And it does something, and maybe you don't know all the details, but you do know that as you approach infinity, you're going to get very, very close to 0. And because it's an even function, you know that the exact same thing happens on the left. We didn't have to say what happens when I plug in a very big negative number because since it was even, we already knew that what happened on the left would be a mirror image of what happened on the right. Now, the book has some harder examples here that I think would be good for you to look at that have some vertical asymptotes that are a little bit more complicated. But I thought this was a pretty good example to do right now in the video. And I hope that you take away at least some of the main ideas. So that's it for this section. We talked about power functions, polynomial functions, and rational functions. Those are 3 important types of functions that we'll use as building blocks once we start in on the calculus in section 2.